Welcome to the video lecture on differential equations, growth and decay. Let's start by reviewing how to solve a differential equation. Let's look at y prime equals 2x over y. Now to solve a differential equation, first let's review what a differential equation is. Differential equation is an equation involving x's, y's, or derivatives of a y. So y primes, y double primes, y triple primes, and so forth. So this is actually a fairly simple one to solve because we can rewrite this as dy dx. I'm going to change the notation y prime to dy dx. And this is called a separable differential equation because you can separate it so that the y's are on one side along with the dy and the x's along with the dx are on the other side. And I'm going to do that by just cross multiplying. So if I multiply, I'm going to get y dy on the left and 2x dx on the right. Now once you've separated your variables, then to solve this, we're going to integrate both sides. And remember that the solution to a differential equation isn't a number, it's a function, it's a curve. It's an equation or family of equations that would satisfy this differential equation, which means it should be some kind of an equation that has as its derivative the formula 2x over y. So we're going to try and solve for this set of curves. The integral of y is y squared over 2, and the integral of 2x would just be x squared. Now normally when we integrate without bounds we get a plus c. So you could think about putting a plus c on the left and a plus c on the right, but if you move one of these c's over to the other side, then those two c's would combine into just a new constant. So it's only necessary to put your plus c on one side of the equation, and it doesn't really matter which side it's on. If you want, you could multiply that 2 over to the other side and make this 2x squared. Again, the 2 would get multiplied by the c, but that just absorbs into a new constant c, so we don't even need to write that 2 in front of the c. If you wanted, you could also finish solving for y by taking a square root of both sides and getting that plus or minus symbol in front. I'm not going to bother. I'm just going to leave it as y squared equals 2x squared plus c. So if I were to take the derivative of this equation with respect to x, the formula that I would end up with for that derivative would be 2x over y. Okay, so this is a family of curves. Now, in many applications, it turns out that the rate of change of a variable y is proportional to the value of y. Now that statement right there means this. The rate of change, which is a derivative, so dy, I'm going to use t in this case, dy over dt is proportional to, means is multiplied by a constant k. You can pick whatever variable you want for that constant, but we're just going to use k here for that constant of proportionality. So when I say that the rate of change is proportional to the value of y, that means the derivative equals a constant times y. And we're going to assume here that y is a function of time t. So if we saw this differential equation, how could we solve for the solutions, the curves that have this equation? Well, let's separate it again. So I am going to take this dt and I'm going to multiply it over to the other side. And I have a y on the right side that I don't want over there because I just want t's on the right side. So let's go ahead and divide both sides by y. So we have dy over y equals k dt. Now y's are on the left. There's really no t variable at all, but I'm going to leave that constant k where it is on the right hand side. And let's go ahead and integrate both sides. Now what's the integral of dy over y? What function has as its derivative 1 over y? Well, that's the ln function, the ln of y. What's the integral of k with respect to t? Well, that would be k times t. And then again, we're going to get that plus c constant over here on the side. So if we wanted to stop here, we certainly could, but I'm going to try and solve for y here to figure out what this function is in terms of t. So in order to solve this for y, I would want to undo this ln, and this is a base e, so I could take e raised to this entire right hand side, and that's what the absolute value of y should equal. So all I did was I undid the ln by rewriting this logarithmic equation into its exponential form. Okay? So when I look at this right-hand side, one thing that you can manipulate here is notice that e to the kt plus c, we have a sum up there in that power. So one thing that I'm going to do is I'm going to break up that sum and make this e to the kt times e to the c. And this is true because when you have the same bases, you get to add powers. So that's why these two statements here are equivalent. And then e to the c, since c is a constant, is just going to be some new constant. So let's call it c again. So we get absolute value of y equals c, I'm going to put that big C in front, e to the kt. So this is what our solution looks like. Now typically in a lot of our application problems we're talking about populations, and usually in those scenarios your y, your population, is going to be positive anyway. So in a lot of situations we can ignore that absolute value and just look at this equation y equals c e to the kt. And one thing that you can notice is that at time 0, if I plug in 0 for this t up here, I'm going to get y equals c e to the k times 0, and e to the 0 goes to 1. So this is called, I'm going to call this initial population, and the subscript that we use for that is usually y sub 0. So this c is going to be that initial population. So this equation becomes y equals y sub 0 e to the kt. So this gives you the population, if that's what you're talking about, at any time t where this y sub 0 is that initial population size. So this is the kind of solution that will satisfy any kind of variable or function or quantity that has a rate of change that's proportional to itself. Okay? So a specific application here would be things like exponential growth with populations or exponential decay with like radioactive isotopes. So we're going to get to that example in just a moment. Let's generalize what we just talked about. So in general, if y is a differentiable function of t such that y is positive and y prime is equal to ky, then for some constant k, y is equal to c e to the kt, where c is that initial value of y and k is called the constant of proportionality. Exponential growth will occur when this k is positive, and exponential decay will occur when that k is negative. So here's a very typical example of exponential decay. Suppose that 10 grams of the plutonium isotope Pu-239 was released in the Chernobyl nuclear accident. How long will it take for the 10 grams to decay to 1 gram? And we're going to have to use the fact that the half-life of this plutonium isotope is 24,100 years. Okay? So if you know that you're talking about exponential growth or decay, then you can automatically assume that your quantity, in this case the amount of plutonium that's there or left, follows this model right here. And I'm going to rewrite this using that y sub 0 notation. So since this is exponential decay, I know that the amount of plutonium that's going to be left, which is what I'm calling y, will have to follow this function. It's modeled by this equation right here. So do we know the initial amount of this plutonium? Well, we are told that we're starting with 10 grams that was released initially. So y sub 0 here is going to be that 10 grams. So I can go ahead and plug that in as my coefficient. We want to know how long it will take for the 10 grams to decay to 1 gram. So 1 gram is an amount, and that's your y variable. So we really want to know what happens if I were to plug in 1 for y. But right now I can't solve that because I still don't know what k is. So we're going to have to use some additional information to find out K first, and then we'll be able to plug in 1 for Y and solve for T. So this additional information that we need is going to be this half-life. We need to know a time and an amount that go together so that we can plug in a T and a Y and solve for K. So that's what this half-life tells us. Half-life means the amount of time that needs to pass in order for you to have half as much of your amount left over. So if we're starting with 10, then in 24,100 years, we will have 5 grams left. So the 5 grams is your Y, your amount. And your time is this 24,100. Now, how do you solve this? This is something that you should be familiar with from college algebra. First thing you want to do before you try to undo that E is always divide through by that coefficient. Get rid of that 10 first. And 5 divided by 10 is just a half. I'm going to write that as 0.5. So we have 0.5 equals E to the 24,100 K. Now to solve this, you need to get past that E and undo it, and that's what an ln does. So I'm going to take the ln of both sides. An ln cancels out an E because the ln of E is just 1. And that's going to leave us with this power that we can bring down because of properties of logs. So to finish solving for K, I just divide by this 24,100 number. And I would recommend in the rest of this problem, I'm actually going to leave it in this exact form. But just to show you the size of this, this is approximately negative 0.000028761. And you can punch that into your calculator to see that. I don't recommend using a decimal approximation in the next step because that really can decrease the accuracy of your final answer. So I recommend leaving K, even though it's tedious, leaving it in this form. So that means I can rewrite this modeling equation right here. Since I now know what K is, I'm going to go ahead and substitute it in. So this is going to be Y equals 10E to the ln of 0.5 over 24,100 times T. And what we wanted to actually solve was how long it takes for there to be 1 gram left. And that's the amount. So we want to put in 1 gram in for this Y. And that means we want to solve this for that T. So just like before you can get at that T and before you can get at that E, you need to get rid of your 10. So always divide by that initial coefficient first. 1 divided by 10 is 0.1. And now I have that E isolated, so now I'm ready to take the ln of both sides. So the ln of 0.1 equals the ln of E to the ln of 0.5 over 24,100. ln and E cancel out, and this whole power comes down. And then to solve for T, we just want to get rid of this coefficient. So what I would recommend, since this is a fraction, is just multiplying both sides by the reciprocal. So I'm going to multiply both sides by 24,100 divided by ln of 0.5. And that'll cross out this, giving me just my T. And then in your calculator, you're just going to type in 24,100 times ln of 0.1 divided by ln of 0.5. And that is approximately 80,059. And our units here are years, since that was the units of our half-life. So it's going to take over 80,000 years for 1 gram of this plutonium to still be around. Okay? All right. Let's try another example. This time we're going to try an exponential growth application. So if you know that you've got a bacteria in a culture that is increasing exponentially, then right away that means we get to use this modeling equation that y equals y sub 0 e to the kt. Okay? Because every kind of exponential growth or exponential decay kind of example is going to have this model. So we are told that there are 125 bacteria in the culture after 2 hours and 350 bacteria after 4 hours. Find the initial population. So we're trying to find this y sub 0. Okay? What we're told is a y and a t that go together and another y and a t that go together. We don't have k and we don't have y sub 0, so we're going to need both of those pieces of information to help us solve this. So here's what we're going to do. First thing we're going to do is we're going to substitute in the values that we know. So there's 125 bacteria, so that's an amount, that's a population, so that goes in for your y, equals to y sub 0 e to the k, and the time for that was 2 hours, so t here is 2. We also know that there are 350 bacteria in our population after 4 hours, so when t is 4. Now this actually creates what's called a system of equations. It's two equations with two variables. It's not a linear system of equations because we've got these exponentials in here, but it still is a system. So what we can try to do to solve this is we can try to be a little bit clever here. What I'm going to do is I'm going to rewrite this. I'm going to do this one on top and rewrite it as 350 y sub 0 e to the 4k, and then underneath it I'm going to write the 125 equals y sub 0 e to the 2k. And we want to solve this. So one thing that I noticed that might help me eliminate one of my variables here is to actually divide the two equations right away. So 350 divided by 125, you could reduce that if you wanted to. I'm just going to leave it as is for now, is what I would get on the left side when I divide. And what do I get on the right side when I divide? Well, when I divide y sub 0 by y sub 0, these actually cancel each other out, which is the whole reason why I'm doing this. I'm trying to eliminate one of my variables. And then what's e to the 4k divided by e to the 2k? Well, when you have two expressions with the same base and you're dividing them, you get to subtract their powers. So this becomes an e to the 4k minus 2k, which is just e to the 2k. So now I'm left with an equation with only one variable, so I should be able to solve for k. So how do I solve for that k? Well, I need to undo this e, and that requires an ln. So ln of 350 over 125 equals ln of e to the 2k. The ln and the e cancel out, just giving me 2k. So when I divide by 2, my k value here is 1/2 ln of 350 over 125. Now, did they want k in part A? No, they wanted initial population. So I'm not quite done yet. What I need to do next is substitute that k back in and then solve for my y sub 0. Now I can plug in that k into this equation here or this one. It doesn't matter. They'll both give me the same solution. It's your choice. So let's just plug it into this top one. So I'll get 125 equals y sub 0 e to the k, which was this 1/2 ln of 350 over 125 times 2, because it was 2 hours for 125 bacteria. So by plugging in this k back into one of these two equations, now I have another equation with only one variable in it, so I should be able to solve for y sub 0. Now when you multiply these two things, the 1/2 will cancel the 2, and what you're left with is e to the ln of 350 over 125. Remember, e's and ln's, when they're right up against each other like this, they cancel each other out. So e raised to an ln is going to cancel out because an ln is the same base. So what you're going to be left with is just that y sub 0 that's out front, and then this 350 over 125 comes down. So then to finish solving, we want to solve for y sub 0, so all I have to do is multiply by the reciprocal. So I'm going to multiply by 125 over 350. So this will be 125 squared over 350 equals my y sub 0, and that, when you substitute it into your calculator, is approximately 45. So there's about 45 bacteria initially. I'm rounding up to the nearest whole number since we're talking about bacteria. Okay? All right. Part B. Determine the number of bacteria after 8 hours. So 8 hours is a time. So this is telling me use time, or t, equal to 8. So what's our modeling equation here? Well, it's coming from this. We now know what y sub 0 is, and we also have solved for k as well. So this model becomes y equals my 125 squared over 350. Again, you can feel free to reduce that if you like. There's my initial population, and then this is e to that k, and here was that k, 1/2 ln of 350 over 125, all raised to the t. So all I need to do is plug in 8 for that t. And this is just a calculator problem. You don't actually have to solve any kind of an equation here. 1/2 of 8 becomes a 4, so you can substitute that in if you like, and just punch it into your calculator. It's actually going to come out nice and even, because if you rewrite this, you don't have to do this. You may certainly do it on your calculator, but I just want to show you that this becomes e to the 4 ln of 350 over 125, and this 4 can be brought up to a power, so that this would become the ln of 350 over 125 to the 4th. And there is that e and that ln again, which are going to cancel out. So this is 125 squared over 350 times 350 over 125 quantity to the 4th. And there's a lot of cancellation that's going to go on there. And the end result is you get a nice even number, 2744. Okay? All right, last question. After how many hours will the bacteria count be 25,000? So this time around, we are being given the bacteria number that we want to end up with, which is a y variable. So this time we're being given y, and we want to know t. So you have to go back to your model right here, and we're going to plug in 25,000 over here where y is. Okay, so we get all of this, and just as before, to get up at that t, we got to isolate this e, which means we need to get rid of its coefficient. So I'm going to multiply this side by the reciprocal, 350 over 125 squared, which will make this go away. So we're going to get 350 times 25,000 over 125 squared equals e to the 1/2 ln of 350 over 125, all raised to the t. Now I'm ready to take my ln of both sides to get rid of that e. So I'm going to take the ln of all of this stuff on the left-hand side, the ln and the e will cancel, giving me 1/2 ln of 350 over 125 times t. And to solve for this t, I'm going to want to undo this coefficient out front. Well, to undo the 1/2 means to multiply by 2. So I'm going to multiply by 2 to the other side to get rid of the 1/2. And then to get rid of this ln, that requires dividing. So I'm going to have to divide all of this by the ln of 350 over 125. So t is going to be 2 ln of 350 times 25,000 over 125 squared, all over ln of 350 over 125, and then punch that into your calculator, and you get approximately 12.3. The units on this should be the same units that were being used throughout the rest of the problem, and these were all given in hours. So this is going to be about a little over 12 hours before our bacteria population reaches 25,000. Okay, the last application that we're going to look at is something called Newton's law of cooling. And what Newton's law of cooling says is that the rate of change in the temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding air. So this is the situation where you might take a hot cup of coffee outside on a cold day where the surrounding air temperature is quite cold. That's going to bring the temperature of the coffee down. So you're going to have that exponential decay in that temperature. Now, what Newton's law of cooling says in terms of calculus is the rate of change, which means derivative. So I'm going to write that as dy dt, or you could also just call it y prime. That derivative is proportional to, so that means is k times, this time it's not proportional to the original amount, it's proportional to the difference between the object's temperature and the temperature of the surrounding air. So the object's temperature is what we're calling this y, and I'm going to let the temperature of the surrounding air be y sub s, and we want the difference between these two things. So Newton's law of cooling has this equation for its differential equation. This is what the differential equation is for Newton's law of cooling. So let's take a look at an example. A container of hot liquid is placed in a freezer that is kept at a constant temperature of 20 degrees Fahrenheit. The initial temperature of the liquid is 160 degrees Fahrenheit. After 5 minutes, the liquid's temperature is 60 degrees. How much longer will it take for the liquid's temperature to decrease to 30 degrees? Okay? So, if we want to use Newton's law of cooling, the only thing we have going for us right now is this differential equation. The fact that y prime, or dy dt, is equal to k times the temperature minus the temperature of the surrounding air. Do we know in this problem the temperature of the surrounding air? Yes, because we're putting this liquid in a freezer that has a constant temperature of 20 degrees. So 20 is going to go right here where this y sub s is. Now let's solve this differential equation so we can use the correct model for solving the rest of the problem. We need some sort of equation model, like our y equals y sub 0 e to the kt. We need something like that that we can use to plug in some times and some temperatures. So we have to solve this differential equation first. So first thing I'm going to do is move this dt over, and then I notice that this quantity y minus 20 has a y in it, so I want to move that over to the left side by dividing. So we're going to get dy over y minus 20 equals k dt. Now we're ready to integrate. So on the left side, we don't have just dy over y, we have dy over y minus 20. But if you think of that denominator, that stuff in the bottom as y minus 20, then stuff prime is just a 1, which we do have in that numerator. So this is stuff prime over stuff, which means this antiderivative is just an ln. It's going to be the ln of the absolute value of that denominator, y minus 20. And then this is going to equal the antiderivative of k, which will just be kt plus some constant c. Now I want to get rid of this ln and try to solve this for y. So remember, ln is a base e. So to rewrite this logarithmic equation in its exponential form, I'm just going to take base e and raise it to this right-hand side. And I'm going to be left with this absolute value of y minus 20 on the left-hand side. Now we can assume in this problem that the temperature of our object is going to stay at 20 degrees or higher because the temperature of the freezer is 20 degrees. You can't get colder than that inside of that freezer. So what that implies, since our y is going to be greater than or equal to 20 degrees, is that this quantity, this difference right here, will always be positive. So that just allows me to drop those absolute values. On the other side, we're going to pull the same trick we did earlier. We're going to break this up into e to the kt times e to the c and just label this e to the c as a new constant, big C. So this right-hand side is just c e to the kt. And now if I add 20 to the other side, I now have a model. Okay, so this is my new temperature model. What I would like to do is eliminate that C so that I have one less variable to deal with. So let's think about what our initial temperature is at time 0. So when the time is 0, when that temperature, when that container of hot liquid is initially placed into this freezer, what is that initial temperature? 160 degrees. So initially at time 0, this temperature is 160. So I'm going to use 160 for my y. I'm going to use 0 for my t, and I'm going to plug that into this equation, and hopefully it will enable me to solve for c. And it does, because e to the 0 goes to 1. So this just becomes c plus 20 equals 160. And when I subtract that 20 to the other side, that tells me that c is 140. So my model up here, I'm going to write it over here now, is y equals c, which we just solved for and found out to be 140, e to the kt plus 20. So that's the model I want to use. I still need to find out k. So that's what this first set of data is going to allow me to do. After 5 minutes, the liquid's temperature is 60 degrees. So when t is 5, y is 60. So let's plug in 60 for y and 5 for t. And now we should be able to solve for that k. First things first, you need to isolate this e. Now this time we have a plus 20 on the side. You have to move that over first. So I'm going to subtract 20, which gives me 40. And then I want to further isolate this e by dividing by that 140 out front. Get rid of that coefficient. So a couple zeros are going to drop, and if I divide by 2, this becomes 2/7 e to the 5k. Now that that e is isolated, I can take my ln of both sides. The ln and the e cancel out, giving me just 5k. And if I divide by 5, then now I know that k is 1/5 ln of 2/7. So this model becomes y equals 140 e to the 1/5 ln of 2/7 times t plus 20. So now my only variables are t and y. So I should be able to answer the final question, which is how much longer will it take for the liquid's temperature to decrease to 30 degrees? So if I plug in 30 degrees for my end temperature here, I want my y to be 30. So we want to solve this for t. So just like before, first thing you have to remove is the 20, so I'm going to subtract it and just get a 10. And then I want to get rid of that coefficient that's out front. So I'm going to go ahead and divide by 140. So a couple of zeros will cancel out, and I'll get 1/14 equals e to the 1/5 ln of 2/7 times t. And if I take the ln of both sides, then the ln and the e will cancel, giving me just 1/5 ln of 2/7 times t. So to solve this, or finish solving for this, I'm going to get rid of the 1/5 by multiplying by 5, and I'm going to get rid of this ln of 2/7 by dividing. So there's my t. All of this is my t. And if you punch it into your calculator, what are we going to get? So here's what it's going to look like when I type it into my calculator. I have 5 in parentheses, 5 ln of 1/14 divided by ln of 2/7, and we get about 10.53. So when we look at the way the question is worded up here, it says, how much longer will it take for the liquid's temperature to decrease to 30 degrees? And this is coming right after the sentence that says after 5 minutes, the liquid's temperature is 60 degrees. So if we subtract off that initial 5 minutes that it took to get to 60 degrees from our 10.5, then that means we're going to be left with about 5.5 minutes. So this time was about 10.53 minutes, taking off that initial 5 minutes. So it's going to take another additional 5.5 minutes to get to 30 degrees. Okay? All right, so exponential growth and decay. That concludes our lecture on differential equations, growth and decay. Good luck!